We know the universe had a beginning. A moment 13.8 billion years ago when it sprang into life, creating the vast cosmos we see today. Now we've discovered its origin, we're faced with another equally fundamental question.
If the universe has a beginning, if it was born, does that then mean it'll eventually die? Or will it just keep on going forever, eternal? You see, for us, as all too mortal humans, the ultimate fate of the universe is a question that's hardwired into our psyche. Trying to answer it has driven an astonishing revolution in our understanding of the cosmos.
Yet in recent years, it's also revealed a universe that's far stranger than we ever imagined, and led to one of the most shocking moments in scientific history. It's the latest twist in a tale stretching back over 100 years. In that time, key experiments and crucial discoveries.
And there it is. Exactly where Hoyle predicted.
Have brought us closer than anyone thought possible to finally knowing the ultimate fate of the universe. The sheer scale of the universe is truly staggering. How on earth can you predict the future of something so vast, so complex, so much bigger than we are? Since we first started grappling with this question, the answer has hinged on one simple idea.
If we could chart, observe, and understand how the universe has changed, how it has evolved to the present moment from its very ancient beginnings, then we should be able to extrapolate forward and predict how it will evolve in the future. Unfortunately, the slight flaw in that plan is that the universe operates on timescales of millions and billions of years. We don't.
To understand the workings of the universe, we need to see beyond our limited human lifespan. And in this case, it turned out the sheer scale of the universe could be turned to our advantage. The universe is so vast, light from some of the objects we see in the night sky has taken millions, even billions of years to reach the Earth. When we look up, we're looking back in time at a record of the deep history of the universe.
The problem is we only have a snapshot. A single complex and confusing picture of all this history. It's like taking all the words in a novel, jumbling them up and sticking them on a single page. The key is to try and unpick this story, to learn how to read it, to recognize and understand what's going on.
Astronomers realized that stars could help unlock that history.
If scientists could work out how stars change, how they evolve in time, they could begin to understand the bigger story of how the universe was changing, the first clues to what the future might hold.
But it would take until the middle of the 20th century to find the answer.
Unlocking the secrets of the stars would take a moment of brilliance from this man, Fred Hoyle. Hoyle was a brilliant mathematician and physicist, one of the greatest of his day. He was creative, coming up with bold theories. Above all, he loved a problem, some thorny issue he could make his mark by solving. And in the late 1940s, he found one of the biggest.
Hoyle wanted to know where the elements came from. The early universe was mostly just a sea of hydrogen and helium, the simplest and lightest elements. But we know that changed.
Look around us now. This is no simple world we live in. We're surrounded by complexity, built from complex, heavy elements like the oxygen I breathe and the iron in our blood, and of course carbon in the trees and in every cell in my body. No one knew how to bridge the gap, how the universe went from that very simple beginning to all of this. This was the problem Hoyle seized on.
Hoyle knew nuclear fusion must hold the answer. In nuclear fusion, lighter elements are fused together to make more complex ones. It was already known to happen in the heart of stars, where hydrogen fused together to form the more complex helium. Hoyle wondered how to go further, how the helium nuclei might fuse to make heavier elements.
It's a remarkably simple idea. Here's our helium nucleus. If you could stick together two helium nuclei, you'd make beryllium, a heavier, more complex nucleus. Then add a third helium nucleus and you get carbon. From there you can carry on building up heavier and heavier elements. It sounds like the perfect solution, but there was a very good reason why the formation of carbon, hence all other elements, was still such a big mystery.
The problem was that the physics of this process just didn't work. Calculations showed that three helium nuclei wouldn't stick together. The carbon nucleus they formed was unstable and simply fell apart.
If it broke down at carbon, then there was no chance of making any other heavier elements. It was like hitting a roadblock every time.
In typical bold and bullish fashion, Hoyle got around the problem by predicting a brand new state of carbon.
Hoyle took an intuitive leap. He decided that if three helium nuclei did come together inside a star, they could form carbon with a bit more energy than normal. In this special state, it could stay intact for just long enough to become stable. In that way, stars could make carbon, and the roadblock was removed.
If he was right, then Hoyle had solved the mystery. The elements were built in the heart of stars. But there was more at stake than that. Hoyle realized his theory could reveal how stars changed through their lives. And as the universe we see is built of stars, that would make it a powerful tool for predicting the future of the universe. Astronomers were already grouping stars based on their size, colour and brightness, plotting them on a chart that was known as the Hertzsprung-Russell diagram.
So here we have the diagram they created. Along here is size and brightness, running from very large, very bright stars all the way down to smaller, dimmer stars. And along this direction is colour and temperature. Very hot blue stars all the way down to cooler red stars.
Most regular-sized stars fell into a long diagonal through the middle of the diagram, with a group of giant bright stars above and small dwarf stars below. Astronomers could see the patterns, but weren't able to unlock what they meant, until Hoyle and his theory presented a radical new way of looking at the diagram, one that would reveal the life cycle of a star.
Let's consider our own sun. Now, at the moment, it's sitting here in the middle of the diagram, happily burning hydrogen, turning it into helium. But if Hoyle was right, when it's run out of its hydrogen, it'll start fusing helium to make heavier elements. Now, at this point, a dramatic transformation takes place, because rather than moving down the diagram in this direction, it expands to many times its size and jumps across here to live amongst the red giants. At this phase, it starts burning helium to make much heavier elements
until it finally begins to produce carbon.
Now, at that point, when it's run out of its nuclear fuel, it undergoes its final transformation. It sheds most of its outer layer and leaves behind a tiny white cinder living here amongst the white dwarfs. All stars follow their own route around the diagram. Hoyle's theory provided the understanding to track each star's evolution, driven by the sudden ignition of a new phase of elemental formation.
Here was the answer to the mystery of the heavy elements, the key to the life cycle of the stars, and a window onto the future of the universe, all thanks to Hoyle's new state of carbon. There was just one slight problem.
No one had ever seen or detected Hoyle's special form of carbon, not in the telltale spectra from stars, not anywhere on Earth, not even in a laboratory experiment. As far as anyone could tell, it didn't exist. And without this special form of carbon, the whole theory would come crashing down.
What happened next is a testament to Hoyle's brilliance and almost pig-headed self-belief. In the 1950s, Hoyle joined the California Institute of Technology, Caltech, who had one of the few particle accelerators in existence at the time, similar to this one. Hoyle wanted to use the accelerator to try and make his high-energy carbon. They were not so keen. Here was an unknown Brit trying to take over their new machine in order to look for something he'd effectively made up.
Like Hoyle, I'm a theorist. Experimental physics is a very different world, and it's a different area of expertise. But Hoyle had the confidence, the daring to stride into the lab and, as the director of the facility said, without a buy or leave, demand that they give up the research they were doing in favor of carrying out a complicated experiment to look for something that no one even believed existed in the first place. I'm pretty sure I wouldn't have had the guts to do that.
Hoyle kept at them, arguing it will be a crucial and famous discovery. Finally, they gave in. The search was on. Today, I'm recreating their experiment.
The plan was to bombard a target element with a particle beam to see if they could create that state of carbon. Well, I have with me my own experimental colleagues, Zani and Robin, to help me out.
Our target will be held in the center of this reaction chamber.
Now, what they were looking for was a very specific signal that would show up in their detectors. If that state of carbon existed, then Hoyle predicted that it would show up as a spike in the energy at 7.7 million electron volts, the fingerprint of this special state of carbon.
We'll be looking for the same spike in energy. Time to seal the chamber, close the radiation doors, and see for ourselves what happened.
Right, this is the control panel, and they've let me in, a theorist, to get it all running. So the first thing I do is fire up the beam, then to aim the beam at the target.
Charged particles are now slamming into the target. Back in the 1950s, this was Hoyle's moment of truth.
Now, data will start coming in, and the important display to look at is over here. Now, if Hoyle was right, they'd see his excited state of carbon at this energy here. They would expect to see a spike in energy at that point. And there it is. Exactly where Hoyle predicted. Now, when this experiment was carried out some 60 years ago, they were flabbergasted to see that Hoyle was right. It's quite incredible to think that he just worked on a theoretical hunch, convinced his experimental colleagues to do the experiment, and he was right.
He was also right about the fame. The director of the laboratory went on to receive the Nobel Prize for the discovery. Hoyle, however, received nothing. They published their findings in one of the most famous and heavily referenced papers in science.
On the front cover of the paper, the authors put a very apt quote from Shakespeare's King Lear. "It is the stars above us, govern our conditions." It was the confirmation of this excited state of carbon that proved that it's inside stars that all the elements that make up the world around us, including ourselves, are actually forged. And with that discovery, we gained real insight into the life cycle of stars. We could begin to understand how the universe changed over time, both now and into the future.
Here was the foundation for extrapolating into the future. And it made one clear prediction for the end of the universe.
It was hydrogen and helium that first formed stars. And it was these two elements that were consumed in stars as they aged, creating all the heavier elements in the process. The logical conclusion was disturbing. After an almost unimaginable length of time, stars would use up all the hydrogen and helium in existence. No new stars could form, and existing stars would eventually run out of their fuel and die. The universe would go dark.
For everything that's important to you and me, the light and life created by the stars, the universe would eventually come to an end. But there was another option, one that promised a very different fate and would play out long before the stars ran out of fuel. A fate that involved a fundamental force of the universe: gravity.
The potential for gravity to define the ultimate fate of the universe was first spotted by one of science's unsung heroes, Vesto Slipher. Little known, his pioneering expert measurements would transform our understanding of the universe.
In the early 1900s, astronomy was entering its golden age, with ever more powerful telescopes trained on the skies. One of the biggest targets of the time was the nebulae.
Nebulae were patches and swirls of light that could be seen in between the stars, and not much was known about these mysterious objects, so astronomers were scrambling to find out as much about them as possible. Slipher was interested in one particular aspect of nebulae, their motion, and for his target, he chose the most famous one of all, Andromeda.
Slipher wanted to be the first to measure how quickly a nebula was moving. The problem was, his was not the best telescope out there, not by a long chalk. But Slipher did have one big advantage over his competitors. He was a superb astronomer.
This telescope is actually the same size as Slipher's. It has a 24-inch mirror. But Slipher would have loved to have got his hands on something like this. You see, what he needed was to get a spectrum, Now, that involves splitting the light from the nebulae into its different wavelengths, the different colours that it's made of. Now, he'd have used something like this. It's a diffraction grating. And I can see it reflects this light and gives me all the different colours of the rainbow. What worried Slipher was that he needed to collect as much light as possible to give him a usable spectrum. And nebulae are exceptionally faint. He feared that getting enough light from his telescope would prove to be impossible.
It may be the same size, but this modern telescope can capture the spectrum of Andromeda in a matter of minutes. With his telescope, Slipher needed 14 hours to produce one spectrum. 2 days of back-breaking effort. 7 hours each night, constantly adjusting the telescope to keep it fixed on Andromeda.
Slipher wanted to know how Andromeda was moving. And for that, he didn't just need the spectrum of light from Andromeda, he needed to have the absorption lines. Now, these are discrete gaps in the spectrum, like this. Now, these absorption lines should always be in the same place if the source isn't moving. If they've shifted to the right towards the red end of the spectrum, that means the source is moving away from us. If they've shifted to the left towards the blue end of the spectrum, that means the source is moving towards us. A blue shift. Now, after 2 days of observing, Slipher was ready to develop his photograph. And he didn't get something as beautiful and clean as this. He got this image. Now, this is in fact blown up. In fact, what he got was a much smaller image than this. And it's not even these lines, top and bottom. In fact, what he got was this dirty smudge in the middle. That was the spectrum from Andromeda. Now, you might think he'd failed, that you couldn't get anything meaningful from this. In fact, not only was he able to get a meaningful measurement, he could work out that Andromeda showed a very clear blue shift, that it was moving towards us. In fact, he worked out it was moving towards us at a speed of 300 kilometers per second, which actually matches modern-day estimates.
Slipher had done it. The first ever measure of the speed of a nebula. His skill and tenacity overcoming the limits of his telescope.
When Slipher presented his findings at an astronomy meeting in 1914, he received a standing ovation. It's often easy to forget how important people like Slipher are. The major breakthroughs in science aren't always about the big idea or the beautiful theory. They're often simply reliant on people who are exceptionally skilled at observing and measuring the natural world.
We now know that the Andromeda Nebula is actually a galaxy, like our own, the Milky Way. And it's Andromeda's movement that reveals how gravity can shape the fate of the universe. Since it was first born in the Big Bang, the universe has been expanding outwards. As a result, most galaxies are actually heading away from each other. When they first formed, the same would have been true of Andromeda and the Milky Way, until gravity got to work and began to overwhelm that expansion.
It's gravity that's dragging Andromeda and our own Milky Way galaxy inexorably together. The question is, if it can pull off this trick in our own little corner of the cosmos, can it do the same over the entire expanse of the universe?
If gravity could overwhelm the expansion, then long before the stars burnt out, our vast universe would inevitably, inescapably collapse in on itself. The universe would end with a big crunch. If gravity failed, the universe would simply continue to expand, far beyond even the time when the last star had died. Everything hinged on one factor, predicted by Einstein's general theory of relativity.
Using general relativity revealed that there were two very different futures to the universe. What's more, they were able to calculate a specific figure that marked the boundary between these two different scenarios. It became known as the critical density.
The critical density was effectively a threshold, based on how much matter and energy, how much stuff there was in the entire universe. If that total was above the critical density, then gravity will drag the entire universe back together into the Big Crunch. If the total was below the critical density, then the expansion of the universe will continue forever.
The fate of the entire universe came down to a simple question. What universe do we live in? One that is above the critical density or one that is below?
One way to tell was to look at the expansion of the universe. If the universe was above the critical density and heading for collapse, then the rate of expansion would already be slowing down. So astronomers began working on a way to measure how the expansion of the universe was changing. They were confident until a precocious PhD student called Beatrice Tinsley spotted a fatal flaw in the plan.
Tinsley, known as Little Beetle to her family and friends, was an extremely talented musician. She could have turned professional, but instead she decided to focus on her other great passion, which was astrophysics. Now, here too she excelled. But an academic career in the 1960s, if you're a woman, wasn't easy. And her institution, the University of Texas, seemed determined to ignore this brilliant scientist in their midst. Despite that, she completed her PhD in less than half the time it would normally take.
And that PhD spelt trouble for the expansion rate measurements. The plan was to measure how galaxies were moving at different distances from Earth, and therefore at different times in the past. How their movement changed would reveal how the expansion of the universe was changing. Measuring the movement was relatively straightforward. It was measuring the distance where the problem lay.
In our everyday world, we're surrounded by visual clues that give us a good sense of scale and therefore of distance. But out in the vastness of the universe, this is much more difficult. So astronomers turn to something that might seem unusual: light itself.
Light is not perhaps an obvious tape measure, but in this case, it seemed ideal.
Now, this relies on a very simple principle. How bright the light appears to me is dependent on how close I am to it. So when I'm very close, a lot of light enters my eyes and it seems bright. But as I move away, the light has had more chance to spread out and less of it enters my eyes, so it appears dimmer. Crucially, this change in the level of brightness follows a very precise mathematical relationship.
And I can use this relationship to calculate distance. If I measure the difference in brightness between a light next to me
220.
And one further away,
About 1.5. I don't know if you can see that, it's quite dark.
I can work out how far away the light is.
And so now I have to divide these two numbers, and it's roughly 150. Now, I had to take the square roots. So the square root of 150, well, it's about 12. It's just over 12, about 12.2 meters. Right.
Now to check my working. It's this principle that astronomers were using to measure the distance to galaxies.
So what I have here is 11.5 meters. Now it's a bit less than the 12 meters I calculated, but close enough. I'm pretty happy with that.
But this technique only works if you know how bright the distant object should be, so you can measure how much that brightness has changed. And that would turn out to be the astronomers' Achilles heel.
They were measuring galaxies at different distances, so at different times during the life of the universe. Now, this meant that the galaxies differed in age by millions or billions of years. You see, for the distance measurements to work, they had to assume that all these galaxies of different ages were shining with the same brightness. In other words, a galaxy's brightness doesn't change over time. But for Beatrice Tinsley, there was a fatal flaw at the heart of this assumption.
Tinsley was fascinated by the life cycle of the stars, how they changed through their lives. Her PhD looked at what effect that would have on the brightness of galaxies.
For Tinsley, it was clear that if stars have a life cycle during which their appearance and indeed brightness change, then because galaxies are fundamentally made of stars, so too would their brightness change over time.
Tinsley's findings sent shockwaves through the field. A palpable sense of panic, as one astronomer of the time described it, and they were immediately challenged.
You see, a huge amount of time, effort and money had been invested in these expansion measurements, and yet here was this unknown young PhD student, a woman no less, who was questioning it all. And yet there was no arguing the logic of Tinsley's work, and after 4 years it was eventually accepted.
With that, it was back to the drawing board. A new way was needed to test how close the universe was to the critical density, to see if it would collapse or continue to expand. There was another option, a more direct approach.
One obvious way to see how close the universe is to the critical density is just to count how much stuff there is out there. It's a simple enough idea, but rather difficult to pull off. After all, in something as almost unimaginably vast as the universe, how do you count every galaxy, every star, every speck of interstellar gas? It's almost impossible.
So, instead, astronomers cut the universe down to size. They took an average count of just one small part and then multiplied it up from there. They could do this thanks to one unique characteristic of the universe.
As far as we can tell, the universe is, on the largest scales, the same in whatever direction we look. So an astronomer sitting here on Earth looking out into space will get pretty much the same view as an alien astronomer on a planet thousands of light years away looking out in a completely different direction. And that's why measuring how much stuff there is in one small part of the universe gives us a pretty accurate measure of how much there is overall.
They took their averages and came up with a total amount of mass and energy in the universe.
The results took everyone by surprise. All of them suggested the universe was well below the critical density. In fact, the best estimates suggested the universe had so little mass that its density was only a tiny fraction of the critical value.
Obviously, if right, then there was no way that the universe was going to collapse. But there was a problem with this first estimate of how close the universe was to the critical density. The results were so low they just didn't make any sense.
A flat white coffee, please. Ours is so clearly a universe of matter, mass and energy. They dominate our world. They are our world. These findings painted a picture of a universe so alien to our everyday experience that it's perhaps understandable it was such a difficult concept to embrace.
What's more, the estimates seem to be at odds with the universe itself. The scale of the mismatch was revealed when the universe was mapped on an unprecedented scale by Margaret Galler at Harvard University.
What Galler and her team did was first take a slice of the universe, some 500 million light years long, 300 million light years wide, but still a thin wedge of the visible universe. They observed as many galaxies as they could and plotted them against distance. So every one of these dots is an individual galaxy. There's over 1,000 of them. What took everyone by surprise was this pattern that they saw, these bubbles or almost a honeycomb structure. You see, everyone had assumed that the galaxies would be scattered randomly throughout the universe. Here, for the first time, was evidence that, far from random, the universe actually had structure.
And at the heart of this newly discovered structure was the pull of gravity.
Since almost the beginning of the universe, gravity has been drawing matter together. First into clouds of gas, which then clump together to form galaxies. These galaxies come together to form clusters of galaxies, and the clusters into superclusters. It's like a work of art. These superclusters of galaxies are all joined together by filaments of dust and gas, all acting under the same irresistible pull. My universe has just collapsed. Here we clearly see gravity acting as an architect, shaping and influencing the structure of the entire universe on a truly cosmic scale. No, I think I can do better.
The problem was, the estimates of matter in the universe were so small.
I need to open that up.
They put the universe so far below the critical density that such grand structures simply couldn't form.
I don't like that.
According to the numbers, the universe as we know it couldn't exist.
This is a rubbish universe.
There had to be something missing from the counts. But what was it? And what would it mean for the critical density and the fate of the universe? One of the most colourful and controversial scientists of the 20th century found the first clue. Fritz Zwicky.
Zwicky was an eccentric, abrasive and brilliant scientist, known occasionally to refer to the rest of his profession as spherical bastards, which is basically anyone who's a bastard whichever way you look at him. But even those who disliked him had to admit that he was capable of brilliant work.
Zwicky was also looking at galaxy clusters, and they would lead him to discover something extraordinary.
This picture here is just such a galaxy cluster. It's called Abell 1689. Each one of these yellow dots is part of the cluster. It's quite incredible to think that each one of them is an entire galaxy in itself. It sort of gives you an impression of the sheer scale of these things.
Zwicky was fascinated by what held the clusters together.
The answer, of course, has to be gravity. Imagine these marbles are all each individual galaxies, moving in chaotic orbits around the center of the cluster. but none of them moves fast enough to be able to break free and escape from the cluster.
Because of that, Zwicky could use how fast they were travelling to measure the strength of gravity holding them in place. And the strength of gravity would tell him how much matter, how much stuff there was within the cluster. That's where things got very strange, because the galaxies were moving at tremendous speeds.
The strength of gravity needed to hold all these speeding galaxies within the cluster required far more mass than he could see. And it wasn't just a small difference. In fact, he needed something like 100 times more mass than could be detected.
Zwicky called this mysterious mass dunkle Materie, dark matter. Here was a strong candidate for the missing mass of the universe. But to know if it took the universe above or below the critical density, they had to solve one major problem: how to study something when there's no known way of detecting it.
The answer would come thanks to a discovery made here at the Jodrell Bank Observatory. This giant dish is the Bernard Lovell Radio Telescope, and in 1973 it spotted something no one had ever seen before.
At the time, it was carrying out a survey of some very distant, very bright objects, quasars. Partway through the survey, they detected something very unusual. I've come here today to take another look at what they saw, this time using not just the telescopes here at Jodrell, but radio telescopes across the country.
Right, here we are, the control room at Jodrell Bank. A lovely view there of the Lovell telescope. Now, over here, on these screens, we see live data coming in from various telescopes. One of them, the Mark II, is a radio telescope here at Jodrell Bank, but the rest are scattered around the country, all linked together through optical fibres feeding into the central computer here. Now, the point is, the longer you observe an object, the better quality image you get. And after 50 hours of observation, here's what they see. This is the same image as was seen 40 years ago, showing these two bright dots, two quasars. Now, this wasn't the first time quasars had been seen, but certainly the first time they'd been spotted so close together, as though they were a pair.
A pair was something new. They began to gather as much information about them as possible, including measuring their spectra, the unique fingerprint contained within their light.
Here are the spectra from the two quasars. Now, even at first glance, I can tell they look quite similar. In fact, they're much more than just quite similar. When they first measured them, they saw that they were both redshifted to longer wavelengths by exactly the same amount. And have a look at these emission peaks here. They both fall at exactly the same wavelengths. In fact, the spectra were so similar, they thought they'd made a mistake, that they'd looked at the same object twice. But they hadn't. And that left just one possibility. What they thought were two separate quasars were in fact just one single quasar that had somehow been split into two images. A case of astronomical double vision.
There was a theory that could explain this. A strange effect predicted by Albert Einstein: gravitational lensing.
If you look through this lens, you see that everything behind it is warped into strange shapes. This bizarre effect is because as light passes through different thicknesses of the glass, it bends, giving rise to a warped image. Now, Einstein said that matter, stuff, also warps space, changing the very shape, the fabric of the universe. And so, as light passes through regions of space with high concentrations of matter, it will bend, just like it does going through the glass of this lens, and so giving rise to similar visual tricks.
How much the light is bent is dependent on how much the space is being warped, and that depends on how much mass there is. Between the quasar and the telescopes, there had to be a huge amount of mass, bending the light so much that the image is split, making the single quasar appear as two.
Here's our culprit, or at least part of it. This smudge here is just one galaxy within a cluster of galaxies that sit between us and the distant quasar. So it's not just a little bit of mass, but hundreds of galaxies, each with billions of stars. Combined, they bend the light from the quasar, giving us the double image.
And the double image was crucial to the study of dark matter. Even with all the mass and matter contained in the galaxy cluster, there wasn't enough to bend the light that much. For that, you needed Zwicky's mysterious and invisible dark matter. And carefully analysing exactly how much the light was distorted could reveal where that dark matter was.
This is what you get, a map. In the centre is the normal matter of the galaxy cluster itself, but surrounding it, stretching out much further, coloured here in red, is the dark matter. Look how far out it spreads. It completely dwarfs the normal matter of the galaxy cluster. Zwicky's mysterious and invisible matter revealed by a cosmic optical illusion.
It couldn't reveal what dark matter was, but mapping like this, as Jodrell is still doing to this day, did give an idea of how much there was out there, and it seemed to far outweigh normal matter. But was it enough to take the universe over the critical density?
Even though there appeared to be far more dark matter than normal matter, that still seemed to leave the universe way below the critical density. But this was still far from the end of the story. The discovery of dark matter had taken the scientific community completely by surprise. Trying to work out how close the universe was to the critical density was just throwing up more mysteries than answers.
A shocking new discovery that initially promised to finally reveal the fate of the universe instead threw physics into crisis. In the 1990s, these telescopes were part of an international project looking to finally reveal the fate of the universe. They were using a new technique to, once again, look at how the expansion of the universe had changed over time. I've come to use this telescope, the GTC, to observe the object that was at the heart of those studies.
This huge telescope, you can see the vast mirror behind it, is going to take a close look at a supernova, the explosive death of a star. The light reaching us from these distant epic events would be key to unlocking how the universe expanded in the past, and in turn would reveal what would happen to it in the future.
To measure the expansion, researchers were interested in a particular type of supernova.
Our target tonight is the same class of supernovae that they were searching for, a Type 1a. Now, what made Type 1a supernovae so useful is that when they went off, they created an incredibly bright spike of light. Briefly, the star would shine brighter than its entire galaxy. Not only that, but they always gave off almost exactly the same level of brightness. This meant that not only could they see them over vast distances in remote galaxies, but they could also work out exactly how far away they were. So if they could find enough of them, they could sample conditions in the universe over a wide range of distances and times.
Tonight, astronomer David Alvarez has been homing in on a recently discovered Type 1a supernova.
Right, David, this is very exciting. Do you have the supernova?
This is the image of the supernova.
That thing there?
That thing there.
Can you zoom in at all on that?
Yeah, we can zoom in here, and you can see the bright dot.
And the rest of it is the galaxy?
The rest of the light you can see there is the host galaxy of the supernova.
I mean, that's incredible. Here's a galaxy with hundreds of billions of stars, but this one exploding star, this one supernova is shining brighter than the whole of the rest of the galaxy. And you know how far away this supernova is. You've measured the distance.
Yeah, the supernova is about 8 billion light years away.
Wow.
As well as the distance, the spectrum of the supernova is also crucial.
The astronomers needed the spectrum of the light because it gave them the redshift. You see, as the light travels from the distant supernova to Earth, the universe is expanding. The space the light is traveling through is stretching, and so the light itself is also stretching. Its wavelength is getting longer. If it leaves the supernova at a particular wavelength, a particular color, when it arrives in our telescopes, it's at a longer wavelength. It's shifted towards the red end of the spectrum, hence a redshift. So knowing the redshift of the light tells us how much space has expanded in that time. In a sense, it gives us a measure of how big the universe has become.
Because of this, measuring redshifts at greater distances, in effect further back in time, could create a potted history of how the expansion of the universe was changing. Astronomers were convinced that gravity must have, at the very least, been slowing down the expansion. The question was by how much? By plotting distance against the redshift measure of expansion, they could finally answer that question.
Now, if we imagine the universe has been expanding at the same rate, the rate that it is now for its entire history, I'd get a very simple line. But astronomers knew this couldn't be correct because, of course, gravity is putting the brakes on the expansion. So the expansion of the universe should be slowing down. And if it's expanding more slowly now, it should have been expanding more quickly in the past. Space stretching more would mean a bigger redshift. Now, what does this mean for our supernova? Well, we know it was 8 billion light years away. So we know it wouldn't fall exactly on this line, which corresponds to a redshift of about 0.49. It should sit maybe somewhere over here, maybe at a redshift greater than 0.5. That means this line should really be curving down like that. But of course, the exact shape of this line would tell them how much gravity is slowing down the expansion of the universe. And that would tell them the fate of the universe. Okay, so David, you have the spectrum ready now.
We have it. Yes, bring it up. Yeah.
And that gives you a measure of the redshift. So what did you measure that to be here?
For this case, we measure a 0.47.
0.47. Well, that puts it on this side of the line. That means it's not a larger redshift, but a smaller redshift. This is fascinating because it's exactly what they saw. Not redshifts that were larger, but redshifts that were smaller. And they saw this time and time again, and it could only have one explanation. Smaller redshifts meant that the universe must have been expanding more slowly in the past than it is today. In other words, rather than slowing down, the rate of expansion of the universe is accelerating.
As more and more supernovae were plotted, the picture became clearer. For the first few billion years after the Big Bang, it looked as if the expansion rate had been slowing, as expected. But then that changed, and the expansion started to accelerate.
It's hard to stress how much of a shock this was. Back then, everyone knew that the expansion of the universe had to be slowing down. Now, whether it would slow down enough to stop and then recollapse, that wasn't clear. But it had to be slowing down. After all, gravity had to be doing its job of putting the brakes on. But it wasn't. About 6 billion years ago, the expansion started to speed up. Clearly there was some new and unexpected thing going on in the universe, something that science didn't have an answer for. Something that was pushing the expansion of the universe at an accelerating rate. It became known, for want of another term, as dark energy.
The best estimates suggest that dark energy makes up 70% of the universe. And that means the universe will not collapse and end in a big crunch. Instead, dark energy, not gravity, will define the ultimate fate of the universe.
Dark energy pushes the universe apart. It won't carry on expanding steadily forever. Instead, dark energy forces the universe to fly apart at an ever-increasing rate. Galaxies will become so far apart that light wouldn't be able to travel between them. Each one will end up as an individual island of stars alone in the cosmos. It may even become so extreme that galaxies themselves will be ripped apart, leaving individual stars all alone in the black emptiness.
Then again, maybe not. After all, the effects of dark energy seemed to suddenly appear between 6 and 7 billion years ago. Who's to say how it'll behave in the future? That may sound bizarre, but with the discovery of dark energy, all bets are off.
It's hard to stress how little we know about dark energy. It has a name, but that's about it. We don't know what it's made of, why it's driving the universe apart, and crucially, how it'll behave in the future. And that leaves a big hole in our understanding of the universe and its ultimate fate.
Dark energy may simply be part of the universe, built into the way it works. Or it could point to a fundamental problem with the most important and trusted scientific theories we have. Ones that are at the very heart of our understanding of how the world works.
How the universe will end started as astronomy's great challenge, but the fate of the universe has become much more than just an academic question. Through the discovery of this strange enigmatic energy, if indeed that's what it is, one that defies current understanding, it spread to the heart of fundamental physics. Finding the answer to how the universe will end could have profound implications on how we understand our world. If you want to find out more about the universe and the end of time, go to the address below and follow the links to the Open University.
Coming up next tonight here on BBC4, exploring our clockwork dreams with a closer look at some mechanical marvels. Stay with us.